person is shown blowing into a tube connected to a plastic bag. There is a computer screen displaying data that reads, Mass spectral breath analysis. An arrow from the plastic bag points to an illustration of different molecular compounds contained in the person's exhalation. Figure 2.1. Analysis of molecules in an exhaled breath can provide valuable information, leading to early diagnosis of diseases or detection of environmental exposure to harmful substances. Credit: Modification of work by Paul Flowers. Chapter outline. 2.1 Early ideas in atomic theory. 2.2 Evolution of atomic theory. 2.3 Atomic structure and symbolism. 2.4 Chemical formulas. 2.5 The periodic table. 2.6 Ionic and molecular compounds. 2.7 Chemical nomenclature. Lung diseases and lung cancers are among the world's most devastating illnesses, partly due to most non-invasive screening procedures aren't reliable, and patients often resist more accurate methods due to discomfort with the procedures or with the potential danger that the procedures cause. But what if you could be accurately diagnosed through a simple breath test? Early detection of biomarkers, substances that indicate an organism's disease or physiological state, could allow diagnosis and treatment before a condition becomes serious or irreversible. Recent studies have shown that your exhaled breath can contain molecules that may be biomarkers for recent exposure to environmental contaminants or for pathological conditions ranging from asthma to lung cancer. Scientists are working to develop biomarker fingerprints that could be used to diagnose a specific disease based on the amounts and identities of certain molecules in a patient's exhaled breath. In Sangeeta Bhatia's lab at MIT, a team used substances that react specifically inside diseased lung tissue. The products of the reactions will be present as biomarkers that can be identified through mass spectrometry, an analytical method discussed later in the chapter. A potential application would allow patients with early symptoms to inhale or ingest a sensor substance and, minutes later, to breathe into a detector for diagnosis. Similar research by scientists such as Laura Lopez Sanchez has provided similar processes for lung cancer. An essential concept underlying this goal is that of a molecule's identity, which is determined by the numbers and types of atoms it contains and how they are bonded together. This chapter will describe some of the fundamental chemical principles related to the composition of matter, including those central to the concept of molecular identity. Learning objectives. By the end of this section, you will be able to state the postulates of Dalton's atomic theory. Use postulates of Dalton's atomic theory to explain the laws of definite and multiple proportions. The earliest recorded discussion of the basic structure of matter comes from ancient Greek philosophers, the scientists of their day. In the 5th century BC, Leucippus and Democritus argued that all matter was composed of small, finite particles that they called atomos, a term derived from the Greek word for indivisible. They thought of atoms as moving particles that differed in shape and size, and which could join together. Later, Aristotle and others came to the conclusion that matter consisted of various combinations of the 4 elements, fire, earth, air, and water, and could be infinitely divided. Interestingly, these philosophers thought about atoms and elements as philosophical concepts, but apparently never considered performing experiments to test their ideas. The Aristotelian view of the composition of matter held sway for over 2,000 years, until English schoolteacher John Dalton helped to revolutionize chemistry with his hypothesis that the behavior of matter could be explained using an atomic theory. First published in 1807, many of Dalton's hypotheses about the microscopic features of matter are still valid in modern atomic theory. Here are the postulates of Dalton's atomic theory. Matter is composed of exceedingly small particles called atoms. An atom is the smallest unit of an element that can participate in a chemical change. An element consists of only one type of atoms, which has a mass that is characteristic of the element and is the same for all atoms of that element. Figure 2.2. A macroscopic sample of an element contains an incredibly large number of atoms, all of which have identical chemical properties. The left image shows a photograph of a stack of pennies. The right image calls out an area of one of the pennies, which is made up of many sphere-shaped copper atoms. The atoms are densely organized. Figure 2.2a pre-1982 copper penny, left, contains approximately 3 times 1022 copper atoms. Several dozen are represented as brown spheres at the right, each of which has the same chemical properties. Credit: Modification of work by SLGCKGC Flicker. atoms of one element differ in properties from atoms of all other elements. A compound consists of atoms of two or more elements combined in a small whole number ratio. In a given compound, the numbers of atoms of each of its elements are always present in the same ratio. Figure 2.3. The left image shows a container with a black, powdery compound. The right image calls out the molecular structure of the powder, which contains copper atoms that are clustered together with an equal number of oxygen atoms. Figure 2.3. Copper 2 oxide, a powdery black compound, results from the combination of two types of atoms, copper, brown spheres, and oxygen, red spheres, in a 1:1 ratio. Credit: Modification of work by Chemical Interest / Wikimedia Commons. Atoms are neither created nor destroyed during a chemical change, but are instead rearranged to yield substances that are different from those present before the change. Figure 2.4. The left stoppered bottle contains copper and oxygen. There is a callout, which shows that copper is made up of many sphere-shaped atoms. The atoms are densely organized. The open space of the bottle contains oxygen gas, which is made up of bonded pairs of oxygen atoms that are evenly spaced. The right stoppered bottle shows the compound copper 2 oxide, which is a black, powdery substance. A callout from the powder shows a molecule of copper 2 oxide, which contains copper atoms that are clustered together with an equal number of oxygen atoms. Figure 2.4. When the elements copper, a shiny red-brown solid shown here as brown spheres, and oxygen, a clear and colorless gas shown here as red spheres, react, their atoms rearrange to form a compound containing copper and oxygen, a powdery black solid. Credit Copper, modification of work by http://images-elements.com/copper.php, closing parenthesis. Dalton's atomic theory provides a microscopic explanation of the many macroscopic properties of matter that you've learned about. For example, if an element such as copper consists of only one kind of atom, then it cannot be broken down into simpler substances, that is, into substances composed of fewer types of atoms. And if atoms are neither created nor destroyed during a chemical change, then the total mass of matter present when matter changes from one type to another will remain constant, the law of conservation of matter. Example 2.1. Testing Dalton's atomic theory. In the following drawing, the green spheres represent atoms of a certain element. The purple spheres represent atoms of another element. If the spheres touch, they are part of a single unit of a compound. Does the following chemical change represented by these symbols violate any of the ideas of Dalton's atomic theory? If so, which one? This equation shows that the starting materials of the reaction are two bonded green spheres, which are being combined with two smaller bonded purple spheres. The product of the change is one purple sphere that is bonded to one green sphere. Solution. The starting materials consist of two green spheres and two purple spheres. The products consist of only one green sphere and one purple sphere. This violates Dalton's postulate that atoms are neither created nor destroyed during a chemical change, but are merely redistributed. In this case, atoms appear to have been destroyed. Check your learning. In the following drawing, the green spheres represent atoms of a certain element. The purple spheres represent atoms of another element. If the spheres touch, they are part of a single unit of a compound. Does the following chemical change represented by these symbols violate any of the ideas of Dalton's atomic theory? If so, which one? This equation shows that the starting materials of the reaction are two sets of bonded green spheres, which are each being combined with two smaller bonded purple spheres. The products of the change are two molecules that each contain one purple sphere bonded between two green spheres. Answer. The starting materials consist of 4 green spheres and 2 purple spheres. The products consist of 4 green spheres and 2 purple spheres. This does not violate any of Dalton's postulates. Atoms are neither created nor destroyed, but are redistributed in small whole number ratios. Dalton knew of the experiments of French chemist Joseph Proust, who demonstrated that all samples of a pure compound contain the same elements in the same proportion by mass. This statement is known as the law of definite proportions, or the law of constant composition. The suggestion that the numbers of atoms of the elements in a given compound always exist in the same ratio is consistent with these observations. For example, when different samples of isooctane, a component of gasoline and one of the standards used in the octane rating system, are analyzed, they are found to have a carbon-to-hydrogen mass ratio of 5.33:1, as shown in Table 2.1. Constant composition of isooctane. Sample carbon-hydrogen mass ratio of 14.82 grams, 2.78 grams, 14.82 grams carbon, 2.78 grams hydrogen equals 5.33 grams carbon, 1.00 grams hydrogen. B 22.33 grams, 4.19 grams, 22.33 grams carbon, 4.19 grams hydrogen equals 5.33 grams carbon, 1.00 grams hydrogen. C 19.40 grams, 3.64 grams, 19.40 grams carbon, 3.63 grams hydrogen equals 5.33 grams carbon, 1.00 grams hydrogen. Table 2.1. It is worth noting that although all samples of a particular compound have the same mass ratio, the converse is not true in general. That is, samples that have the same mass ratio are not necessarily the same substance. For example, there are many compounds other than isooctane that also have a carbon-to-hydrogen mass ratio of 5.33, 1.00. Dalton also used data from Proust, as well as results from his own experiments, to formulate another interesting law. The law of multiple proportions states that when two elements react to form more than one compound, a fixed mass of one element will react with masses of the other element in a ratio of small, whole numbers. For example, copper and chlorine can form a green, crystalline solid with a mass ratio of 0.558 grams chlorine to 1 gram copper, as well as a brown crystalline solid with a mass ratio of 1.116 grams chlorine to 1 gram copper. These ratios by themselves may not seem particularly interesting or informative. However, if we take a ratio of these ratios, we obtain a useful and possibly surprising result: a small, whole number ratio. 1.116 grams Cl 1 gram Cu 0.558 grams Cl 1 gram Cu equals 21. This 2-to-1 ratio means that the brown compound has twice the amount of chlorine per amount of copper as the green compound. This can be explained by atomic theory if the copper to chlorine ratio in the brown compound is 1 copper atom to 2 chlorine atoms, and the ratio in the green compound is 1 copper atom to 1 chlorine atom. The ratio of chlorine atoms, and thus the ratio of their masses, is therefore 2-to-1, figure 2.5. Figure A shows a pile of green powder. A callout shows that the green powder is made up of a lattice of copper atoms interspersed with chlorine atoms. The atoms are color-coded brown for copper and green for chlorine. The number of copper atoms is equal to the number of chlorine atoms in the molecule. Figure B shows a pile of brown powder. A callout shows that the brown powder is also made up of copper and chlorine atoms, similar to the molecule shown in Figure A. However, there appears to be 2 chlorine atoms for every copper atom in this molecule. The copper atoms in Figure B bond with both the chlorine atoms and the other copper atoms. The copper atoms in Figure A only bond with the chlorine atoms. Figure 2.5. Compared to the copper-chlorine compound in A, where copper is represented by brown spheres and chlorine by green spheres, the copper-chlorine compound in B has twice as many chlorine atoms per copper atom. Credit A, modification of work by Benja B. M.M., 27 inches / Wikimedia Commons. Credit B, modification of work by Walkerma, Wikimedia Commons. Example 2.2. Laws of definite and multiple proportions. A sample of compound A, a clear, colorless gas, is analyzed and found to contain 4.27 grams carbon and 5.69 grams oxygen. A sample of compound B, also a clear, colorless gas, is analyzed and found to contain 5.19 grams carbon and 13.84 grams oxygen. Are these data an example of the law of definite proportions, the law of multiple proportions, or neither? What do these data tell you about substances A and B? Solution. In compound A, the mass ratio of oxygen to carbon is 1.33 grams O1 GC. In compound B, the mass ratio of oxygen to carbon is 2.67 grams O1 GC. The ratio of these ratios is 1.33 grams O1 GC, 2.67 grams O1 GC equals 12. This supports the law of multiple proportions. This means that A and B are different compounds, with A having 1/2 as much oxygen per amount of carbon, or twice as much carbon per amount of oxygen, as B. A possible pair of compounds that would fit this relationship would be A equals CO and B equals CO2. Check your learning. A sample of compound X, a clear, colorless combustible liquid with a noticeable odor, is analyzed and found to contain 14.13 grams carbon and 2.96 grams hydrogen. A sample of compound Y, a clear, colorless combustible liquid with a noticeable odor that is slightly different from X's odor, is analyzed and found to contain 19.91 grams carbon and 3.34 grams hydrogen. Are these data an example of the law of definite proportions, the law of multiple proportions, or neither? What do these data tell you about substances X and Y? Answer. In compound X, the mass ratio of carbon to hydrogen is 14.13 grams C2.96 grams H. In compound Y, the mass ratio of carbon to hydrogen is 19.91 grams C3.34 grams H. The ratio of these ratios is 14.13 grams C2.96 grams H, 19.91 grams C3.34 grams H, 5.7 grams C per gram H, 5.96 grams C per. This small whole number ratio supports the law of multiple proportions. This means that X and Y are different compounds. Learning objectives. By the end of this section, you will be able to outline milestones in the development of modern atomic theory, summarize and interpret the results of the experiments of Thomson, Millikan, and Rutherford, describe the 3 subatomic particles that compose atoms, define isotopes, and give examples for several elements. If matter is composed of atoms, what are atoms composed of? Are they the smallest particles, or is there something smaller? In the late 1800s, a number of scientists interested in questions like these investigated the electrical discharges that could be produced in low-pressure gases, with the most significant discovery made by English physicist J.J. Thomson using a cathode ray tube. This apparatus consisted of a sealed glass tube from which almost all the air had been removed. The tube contained 2 metal electrodes. When high voltage was applied across the electrodes, a visible beam called a cathode ray appeared between them. This beam was deflected toward the positive charge and away from the negative charge, and was produced in the same way with identical properties when different metals were used for the electrodes. In similar experiments, the ray was simultaneously deflected by an applied magnetic field, and measurements of the extent of deflection and the magnetic field strength allowed Thomson to calculate the charge-to-mass ratio of the cathode ray particles. The results of these measurements indicated that these particles were much lighter than atoms, Figure 2.6. Figure A shows a photo of J.J. Thomson working at a desk. Figure B shows a photograph of a cathode ray tube. It is a long, glass tube that is narrow at the left end but expands into a large bulb on the right end. The entire cathode tube is sitting on a wooden stand. Figure C shows the parts of the cathode ray tube. The cathode ray tube consists of a cathode and an anode. The cathode, which has a negative charge, is located in a small bulb of glass on the left side of the cathode ray tube. To the left of the cathode, it says high voltage and indicates a positive and negative charge. The anode, which has a positive charge, is located to the right of the cathode. 2 charged plates are located to the right of the anode and are connected to a battery and 2 magnets. The magnets are labeled S and N. A cathode ray is generated from the cathode, travels through the anode and into a wider part of the cathode ray tube, where it travels between a positively charged electrode plate and a negatively charged electrode plate. The ray bends upward and continues to travel until it hits the wide part of the tube on the right. The rightmost end of the tube contains a printed scale that allows one to measure how much the ray was deflected. Figure 2.6 A. J.J. Thomson produced a visible beam in a cathode ray tube, B. This is an early cathode ray tube, invented in 1897 by Ferdinand Braun. C. In the cathode ray, the beam, shown in yellow, comes from the cathode and is accelerated past the anode toward a fluorescent scale at the end of the tube. Simultaneous deflections by applied electric and magnetic fields permitted Thomson to calculate the mass-to-charge ratio of the particles composing the cathode ray. Credit A, modification of work by Nobel Foundation. Credit B, modification of work by Eugen Nesper. Credit C, modification of work by Curzon, Wikimedia Commons. Based on his observations, here is what Thomson proposed and why. The particles are attracted by positive plus charges and repelled by negative minus charges, so they must be negatively charged, less massive than atoms and indistinguishable, regardless of the source material, so they must be fundamentals. Although controversial at the time, Thomson's idea was gradually accepted, and his cathode ray particle is what we now call an electron, a negatively charged, subatomic particle with a mass more than 1,000 times less that of an atom. The term electron was coined in 1891 by Irish physicist George Stoney from electric ion. Link to learning. Click here to hear Thomson describe his discovery in his own voice. In 1909, more information about the electron was uncovered by American physicist Robert A. Millikan via his oil drop experiments. Millikan created microscopic oil droplets, which could be electrically charged by friction as they formed or by using X-rays. These droplets initially fell due to gravity, but their downward progress could be slowed or even reversed by an electric field lower in the apparatus. By adjusting the electric field strength and making careful measurements and appropriate calculations, Millikan was able to determine the charge on individual drops, Figure 2.7. The experimental apparatus consists of an oil atomizer which sprays fine oil droplets into a large, sealed container. The sprayed oil lands on a positively charged brass plate with a pinhole at the center. As the drops fall through the pinhole, they travel through X-rays that are emitted within the container. This gives the oil droplets an electrical charge. The oil droplets land on a brass plate that is negatively charged. A telescopic eyepiece penetrates the inside of the container so that the user can observe how the charged oil droplets respond to the negatively charged brass plate. The table that accompanies this figure gives the charge in coulombs or C for 5 oil drops. Oil drop A has a charge of 4.8 times 10 to the negative 19 power. Oil drop B has a charge of 3.2 times 10 to the negative 19 power. Oil drop C has a charge of 6.4 times 10 to the negative 19 power. Oil drop D has a charge of 1.6 times 10 to the negative 19 power. Oil drop E has a charge of 4.8 times 10 to the negative 19 power. Figure 2.7 Millikan's experiment measured the charge of individual oil drops. The tabulated data are examples of a few possible values. Looking at the charge data that Millikan gathered, you may have recognized that the charge of an oil droplet is always a multiple of a specific charge, 1.6 times. 10-19C Millikan concluded that this value must therefore be a fundamental charge, the charge of a single electron, with his measured charges due to an excess of 1 electron, 1 times 1.6 times. 10-19C, 2 electrons, 2 times 1.6 times. 10-19C. Since the charge of an electron was now known due to Millikan's research, and the charge-to-mass ratio was already known due to Thomson's research, 1.759 times, 1011C per kilogram, it only required a simple calculation to determine the mass of the electron as well. Mass of electron equals 1.602 times 10-19C times 1 kilogram, 1.759 times 1011C equals 9.107 times 10-31 kilograms. Scientists had now established that the atom was not indivisible as Dalton had believed, and due to the work of Thomson, Millikan, and others, the charge and mass of the negative subatomic particles, the electrons, were known. However, the positively charged part of an atom was not yet well understood. In 1904, Thomson proposed the plum pudding model of atoms, which described a positively charged mass with an equal amount of negative charge in the form of electrons embedded in it, since all atoms are electrically neutral. A competing model had been proposed in 1903 by Hantaro Nagaoka, who postulated a Saturn-like atom consisting of a positively charged sphere surrounded by a halo of electrons, Figure 2.8. Figure A shows a photograph of plum pudding, which is a thick, almost spherical cake containing raisins throughout. To the right, an atom model is round and contains negatively charged electrons embedded within a sphere of positively charged matter. Figure B shows a photograph of the planet Saturn, which has rings. To the right, an atom model is a sphere of positively charged matter encircled by a ring of negatively charged electrons. Figure 2.8 A. Thomson suggested that atoms resembled plum pudding, an English dessert consisting of moist cake with embedded raisins, plums. B. Nagaoka proposed that atoms resembled the planet Saturn with a ring of electrons surrounding a positive planet. Credit A. Modification of work by Man VYI, Wikimedia Commons. Credit B. Modification of work by NASA, Wikimedia Commons. The next major development in understanding the atom came from Ernest Rutherford, a physicist from New Zealand who largely spent his scientific career in Canada and England. He performed a series of experiments using a beam of high-speed, positively charged alpha particles that were produced by the radioactive decay of radium. Alpha particles consist of 2 protons and 2 neutrons. You will learn more about radioactive decay in the chapter on nuclear chemistry. Rutherford and his colleagues Hans Geiger, later famous for the Geiger counter, and Ernest Marsden aimed a beam of alpha particles, the source of which was embedded in a lead block to absorb most of the radiation, at a very thin piece of gold foil, and examined the resultant scattering of the alpha particles using a luminescent screen that glowed briefly where hit by an alpha particle. What did they discover? Most particles passed right through the foil without being deflected at all. However, some were diverted slightly, and a very small number were deflected almost straight back toward the source. Figure 2.9. Rutherford described finding these results. It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. 1. This figure shows a box on the left that contains a radium source of alpha particles, which generates a beam of alpha particles. The beam travels through an opening within a ring-shaped luminescent screen which is used to detect scattered alpha particles. A piece of thin gold foil is at the center of the ring formed by the screen. When the beam encounters the gold foil, most of the alpha particles pass straight through it and hit the luminescent screen directly behind the foil. Some of the alpha particles are slightly deflected by the foil and hit the luminescent screen off to the side of the foil. Some alpha particles are significantly deflected and bounce back to hit the front of the screen. Figure 2.9 Geiger and Rutherford fired alpha particles at a piece of gold foil and detected where those particles went, as shown in this schematic diagram of their experiment. Most of the particles passed straight through the foil, but a few were deflected slightly and a very small number were significantly deflected. Here is what Rutherford deduced. Because most of the fast-moving alpha particles passed through the gold atoms undeflected, they must have traveled through essentially empty space inside the atom. Alpha particles are positively charged, so deflections arose when they encountered another positive charge. Like charges repel each other. Since like charges repel one another, the few positively charged alpha particles that changed paths abruptly must have hit, or closely approached, another body that also had a highly concentrated positive charge. Since deflections occurred a small fraction of the time, this charge only occupied a small amount of the space in the gold foil. Analyzing a series of such experiments in detail, Rutherford drew 2 conclusions. The volume occupied by an atom must consist of a large amount of empty space. A small, relatively heavy, positively charged body, the nucleus, must be at the center of each atom. Link to learning. View this simulation of the Rutherford gold foil experiment. Adjust the slit width to produce a narrower or broader beam of alpha particles to see how that affects the scattering pattern. This analysis led Rutherford to propose a model in which an atom consists of a very small, positively charged nucleus, in which most of the mass of the atom is concentrated, surrounded by the negatively charged electrons, so that the atom is electrically neutral, figure 2.10. After many more experiments, Rutherford also discovered that the nuclei of other elements contain the hydrogen nucleus as a quote, building block, and he named this more fundamental particle the proton, the positively charged subatomic particle found in the nucleus. With one addition, which you will learn next, this nuclear model of the atom, proposed over a century ago, is still used today. The left diagram shows a green beam of alpha particles hitting a rectangular piece of gold foil. Some of the alpha particles bounce backwards after hitting the foil. However, most of the particles travel through the foil, with some being deflected as they pass through the foil. A call-out box shows a magnified cross-section of the gold foil. Most of the alpha particles are not deflected but pass straight through the foil because they travel between the gold atoms. A very small number of alpha particles are significantly deflected when they hit the nucleus of the gold atoms straight on. A few alpha particles are slightly deflected because they glanced off of the nucleus of a gold atom. Figure 2.10. The alpha particles are deflected only when they collide with or pass close to the much heavier, positively charged gold nucleus. Because the nucleus is very small compared to the size of an atom, very few alpha particles are deflected. Most pass through the relatively large region occupied by electrons, which are too light to deflect the rapidly moving particles. Link to learning. The Rutherford scattering simulation allows you to investigate the differences between a plum pudding atom and a Rutherford atom by firing alpha particles at each type of atom. Another important finding was the discovery of isotopes. During the early 1900s, scientists identified several substances that appeared to be new elements, isolating them from radioactive ores. For example, a new element produced by the radioactive decay of thorium was initially given the name mesothorium. However, a more detailed analysis showed that mesothorium was chemically identical to radium, another decay product, despite having a different atomic mass. This result, along with similar findings for other elements, led the English chemist Frederick Soddy to realize that an element could have types of atoms with different masses that were chemically indistinguishable. These different types are called isotopes, atoms of the same element that differ in mass. Soddy was awarded the Nobel Prize in Chemistry in 1921 for this discovery. One puzzle remained. The nucleus was known to contain almost all of the mass of an atom, with the number of protons only providing half or less of that mass. Different proposals were made to explain what constituted the remaining mass, including the existence of neutral particles in the nucleus. As you might expect, detecting uncharged particles is very challenging, and it was not until 1932 that James Chadwick found evidence of neutrons, uncharged, subatomic particles with a mass approximately the same as that of protons. The existence of the neutron also explained isotopes. They differ in mass because they have different numbers of neutrons, but they are chemically identical because they have the same number of protons. This will be explained in more detail later in this chapter. Learning objectives. By the end of this section, you will be able to write and interpret symbols that depict the atomic number, mass number, and charge of an atom or ion. Define the atomic mass unit and average atomic mass. Calculate average atomic mass and isotopic abundance. The development of modern atomic theory revealed much about the inner structure of atoms. It was learned that an atom contains a very small nucleus composed of positively charged protons and uncharged neutrons, surrounded by a much larger volume of space containing negatively charged electrons. The nucleus contains the majority of an atom's mass because protons and neutrons are much heavier than electrons, whereas electrons occupy almost all of an atom's volume. The diameter of an atom is on the order of 10⁻⁻10 meters, whereas the diameter of the nucleus is roughly 10⁻15 meters, about 100,000 times smaller. For a perspective about their relative sizes, consider this. If the nucleus were the size of a blueberry, the atom would be about the size of a football stadium. Figure 2.11. The diagram on the left shows a picture of an atom that is 10 to the negative 10th power meters in diameter. The nucleus is labeled at the center of the atom and is 10 to the negative 15th power meters. The central figure shows a photograph of an American football stadium. The figure on the right shows a photograph of a person with a handful of blueberries. Figure 2.11. If an atom could be expanded to the size of a football stadium, the nucleus would be the size of a single blueberry. Credit middle, modification of work by Baby Knight, Wikimedia Commons. Credit right, modification of work by Paxson Wolber. Atoms, and the protons, neutrons, and electrons that compose them, are extremely small. For example, a carbon atom weighs less than 2 times 10⁻23 grams, and an electron has a charge of less than 2 times 10⁻19 C, coulomb. When describing the properties of tiny objects such as atoms, we use appropriately small units of measure, such as the unified atomic mass unit U and the fundamental unit of charge E. The unified atomic mass unit is defined as exactly 1/12 of the mass of a single atom of the carbon-12 isotope. More on isotopes is provided later in this section, and is equal to 1.6605 times 10⁻24 grams. The Dalton dA is an alternative mass unit that is equivalent to the U. Many literature resources, including this text, use the older term atomic mass unit, AMU, when referring to the U or the dA. The fundamental unit of charge, also called the elementary charge, equals the magnitude of the charge of an electron, E, with E equals 1.60 2 times 10⁻19 C. A proton has a mass of 1.0073 atomic mass units and a charge of 1+. A neutron is a slightly heavier particle with a mass 1.0087 atomic mass units and a charge of 0. As its name suggests, it is neutral. The electron has a charge of 1- and is a much lighter particle with a mass of about 0.00055 atomic mass units. It would take about 1,800 electrons to equal the mass of one proton. The properties of these fundamental particles are summarized in Table 2.2. An observant student might notice that the sum of an atom's subatomic particles does not equal the atom's actual mass. The total mass of 6 protons, 6 neutrons, and 6 electrons is 12.0993 atomic mass units, slightly larger than 12.00 atomic mass units. This missing mass is known as the mass defect, and you will learn about it in the chapter on nuclear chemistry. Properties of subatomic particles. Name location charge, see unit charge mass, AMU mass. Nucleus minus 1.602 times 10⁻19 1 - 0, 0.0002 times 10⁻24. Proton nucleus 1.602 times 10⁻24 plus 1.6726 times 10⁻24. Neutron nucleus 1.61. The number of protons in the nucleus of an atom is its atomic number Z. This is the defining trait of an element. Its value determines the identity of the atom. For example, any atom that contains 6 protons is the element carbon and has the atomic number 6, regardless of how many neutrons or electrons it may have. A neutral atom must contain the same number of positive and negative charges, so the number of protons equals the number of electrons. Therefore, the atomic number also indicates the number of electrons in an atom. The total number of protons and neutrons in an atom is called its mass number, A. The number of neutrons is therefore the difference between the mass number and the atomic number. AZ equals number of neutrons. Atomic number Z, mass number A minus Z equals number of protons plus number of neutrons. Atoms are electrically neutral if they contain the same number of positively charged protons and negatively charged electrons. And negatively charged electrons. When the numbers of these subatomic particles are not equal, the atom is electrically charged and is called an ion. The charge of an atom is defined as follows. Atomic charge equals number of protons minus number of electrons. As will be discussed in more detail later in this chapter, atoms and molecules typically acquire charge by gaining or losing electrons. An atom that gains one or more electrons will exhibit a negative charge and is called an anion. Positively charged atoms called cations are formed when an atom loses one or more electrons. For example, a neutral sodium atom, Z equals 11, has 11 electrons. If this atom loses one electron, it will become a cation with a 1+ charge. 11 minus 10 equals 1+. A neutral oxygen atom, Z equals 8, has 8 electrons, and if it gains 2 electrons, it will become an anion with a 2- charge. 8 minus 10 equals 2-. Example 2.3. Composition of an atom. Iodine is an essential trace element in our diet. It is needed to produce thyroid hormone. Insufficient iodine in the diet can lead to the development of a goiter, an enlargement of the thyroid gland. Figure 2.12. Figure A shows a photo of a person who has a very swollen thyroid in his or her neck. Figure B shows a photo of a canister of iodized salt. Figure 2.12. A. Insufficient iodine in the diet can cause an enlargement of the thyroid gland called a goiter. B. The addition of small amounts of iodine to salt, which prevents the formation of goiters, has helped eliminate this concern in the U.S., where salt consumption is high. Credit A. Modification of work by Almazi, Wikimedia Commons. Credit B. Modification of work by Mike Mozart. The addition of small amounts of iodine to table salt, iodized salt, has essentially eliminated this health concern in the United States, but as much as 40% of the world's population is still at risk of iodine deficiency. The iodine atoms are added as anions, and each has a 1- charge and a mass number of 127. Determine the numbers of protons, neutrons, and electrons in one of these iodine anions. Solution. The atomic number of iodine, 53, tells us that a neutral iodine atom contains 53 protons in its nucleus and 53 electrons outside its nucleus. Because the sum of the numbers of protons and neutrons equals the mass number, 127, the number of neutrons is 74. 127 minus 53 equals 74. Since the iodine is added as a 1- anion, the number of electrons is 54. 53(1) equals 54. Check your learning. An ion of platinum has a mass number of 195 and contains 74 electrons. How many protons and neutrons does it contain, and what is its charge? Answer: 78 protons, 117 neutrons, charge is 4, plus chemical symbols. A chemical symbol is an abbreviation that we use to indicate an element or an atom of an element. For example, the symbol for mercury is Hg. Figure 2.13. We use the same symbol to indicate one atom of mercury, microscopic domain, or to label a container of many atoms of the element mercury, macroscopic domain. A jar labeled Hg is shown with a small amount of liquid mercury in it. Figure 2.13. The symbol Hg represents the element mercury regardless of the amount. It could represent one atom of mercury or a large amount of mercury. The symbols for several common elements and their atoms are listed in Table 2.3. Some symbols are derived from the common name of the element. Others are abbreviations of the name in another language. Most symbols have 1 or 2 letters, but 3-letter symbols have been used to describe some elements that have atomic numbers greater than 1, 1, 2. To avoid confusion with other notations, only the first letter of a symbol is capitalized. For example, county is the symbol for the element cobalt, but CO is the notation for the compound carbon monoxide, which contains atoms of the elements carbon C and oxygen O. All known elements and their symbols are in the periodic table in Figure 2.26, also found in Appendix A. Some common elements and their symbols. Element, symbol. Aluminum Al iron Fe from ferrum. Bromine bridge lead the Dewey's carbon C red. Potassium Mg et Slivels. Mercury Hg from hydrogentum. Chlorine Cl nitrogen N. Chromium crossing oxygen O. Cobalt county potassium K from aurum stannum. Iodine I zinc. Tin Sn from stannum. However, until the name is recognized by the International Union of Pure and Applied Chemistry, IUPAC, the recommended name of the new element is based on the Latin words for its atomic number. For example, element 106 was called unnilhexium, Un. Element 107 was called unnilseptium uns, and element 108 was called unniloctium uno for several years. These elements are now named after scientists, or occasionally locations. For example, element 106 is now known as Seaborgium Sg in honor of Glenn Seaborg, a Nobel Prize winner who was active in the discovery of several heavy elements. Element 109 was named in honor of Lise Meitner, who discovered nuclear fission, a phenomenon that would have world-changing impacts. Meitner also contributed to the discovery of some major isotopes, discussed immediately below. Link to learning. Visit this site to learn more about IUPAC, the International Union of Pure and Applied Chemistry, and explore its periodic table. Isotopes. The symbol for a specific isotope of any element is written by placing the mass number as a superscript to the left of the element symbol. Figure 2.14. The atomic number is sometimes written as a subscript preceding the symbol, but since this number defines the element's identity, as does its symbol, it is often omitted. For example, magnesium exists as a mixture of 3 isotopes, each with an atomic number of 12 and with mass numbers of 24, 25, and 26 respectively. These isotopes can be identified as 24 megagrams, 25 megagrams, and 26 megagrams. These isotope symbols are read as element mass number and can be symbolized consistent with this reading. For instance, 24 megagrams is read as magnesium-24 and can be written as magnesium-24 or Mg24. 25 megagrams is read as magnesium-25 and can be written as magnesium-25 or Mg25. All magnesium atoms have 12 protons in their nucleus. They differ only because a 24 megagrams atom has 12 neutrons in its nucleus, a 25 megagrams atom has 13 neutrons, and a 26 megagrams has 14 neutrons. This diagram shows the symbol for helium, He. The number to the upper left of the symbol is the mass number, which is 4. The number to the upper right of the symbol is the charge, which is positive 2. The number to the lower left of the symbol is the atomic number, which is 2. This number is often omitted. Also shown is Mg, which stands for magnesium. It has a mass number of 24, a charge of positive 2, and an atomic number of 12. Figure 2.14. The symbol for an atom indicates the element via its usual 2-letter symbol, the mass number as a left superscript, the atomic number as a left subscript, sometimes omitted, and the charge as a right superscript. Information about the naturally occurring isotopes of elements with atomic numbers 1 through 10 is given in Table 2.4. Note that in addition to standard names and symbols, the isotopes of hydrogen are often referred to using common names and accompanying symbols. Hydrogen-2, symbolized 2H, is also called deuterium and sometimes symbolized D. Hydrogen-3, symbolized 3H, is also called tritium and sometimes symbolized T. Table 2.4. Link to learning. Use this Build an Atom Simulator to build atoms of the first 10 elements, see which isotopes exist, check nuclear stability, and gain experience with isotope symbols. Atomic mass. Because each proton and each neutron contribute approximately 1 atomic mass unit to the mass of an atom, and each electron contributes far less, the atomic mass of a single atom is approximately equal to its mass number, a whole number. However, the average masses of atoms of most elements are not whole numbers because most elements exist naturally as mixtures of 2 or more isotopes. The mass of an element shown in a periodic table or listed in a table of atomic masses is a weighted average mass of all the isotopes present in a naturally occurring sample of that element. This is equal to the sum of each individual isotope's mass multiplied by its fractional abundance. Average mass equals I. Fractional abundance times isotopic mass I. For example, the element boron is composed of 2 isotopes. About 19.9% of all boron atoms are 10B with a mass of 10.0129 atomic mass units, and the remaining 80.1% are 11B with a mass of 11.0093 atomic mass units. The average atomic mass for boron is calculated to be boron average mass equals 0.199 times 10.0129 atomic mass units plus 0.801 times 11.0093 atomic mass units equals 1.99 atomic mass units plus 8.82 atomic mass units equals 10.81 atomic mass units. It is important to understand that no single boron atom weighs exactly 10.8 atomic mass units is the Example 2.4. Calculation of average atomic mass. A meteorite found in central Indiana contains traces of the noble gas neon picked up from the solar wind during the meteorite's trip through the solar system. Analysis of a sample of the gas showed that it consisted of 91.84% 20 Ni, mass 19.9924 atomic mass units, 0.47% 21 Ne, mass 20.9940 atomic mass units, and 7.69% 22, mass 21.9914 atomic mass units. What is the average mass of the neon in the solar wind? Solution. Average mass equals 0.9184 times 19.9924 atomic mass units, plus 0.0047 times 20.9940 atomic mass units, plus 0.0769 times 21.9914 atomic mass units, equals 18.36 plus 0.1.69, AMU equals 20.15 atomic mass units. The average mass of a terrestrial neon atom is 20.1796 atomic mass units. This result demonstrates that we may find slight differences in the natural abundance of isotopes, depending on their origin. Check your learning. A sample of magnesium is found to contain 78.70% of 24 megagrams atoms, mass 23.98 atomic mass units, 10.13% of 25 megagrams atoms, mass 24.99 atomic mass units, and 11.17% of 26 megagrams atoms, mass 25.98 atomic mass units. Calculate the average mass of AMG atom. Answer: 24.31 atomic mass units. We can also do variations of this type of calculation, as shown in the next example. Example 2.5. Calculation of percent abundance. Naturally occurring chlorine consists of 35 Cl mass 34.96885 atomic mass units and 37 Cl mass 36.96590 atomic mass units, with an average mass of 35.453 atomic mass units. What is the percent composition of Cl in terms of these two isotopes? Solution. The average mass of chlorine is the fraction that is 35 Cl times the mass of 35 Cl plus the fraction that is 37 Cl times the mass of 37 Cl. Average mass equals fraction of 35 Cl times mass of 35 Cl plus fraction of 37 Cl times mass of 37 Cl. If we let x represent the fraction that is 35 Cl, then the fraction that is 37 Cl is represented by 1.00 minus x. The fraction that is 35 Cl plus the fraction that is 37 Cl must add up to 1, so the fraction of 37 Cl must equal 1.00 minus. Substituting this into the average mass equation, we have 35.453 atomic mass units, 35.453 1.99705x, x equals x times 34.96885 atomic mass units, plus 1.00 minus x, 34.705 equals 0.7576. So solving yields x equals 0.75. Therefore, chlorine consists of 75.76% 35 Cl and 24.24% 37 Cl. Check your learning. Naturally occurring copper consists of 63 Cu mass 62.9296 atomic mass units and 65 Cu mass 64.9278 atomic mass units, with an average mass of 63.546 atomic mass units. What is the percent composition of Cu in terms of these two isotopes? Answer: 69.15% Cu63 and 30.85% Cu65. Link to learning. Visit this site to make mixtures of the main isotopes of the first 18 elements, gain experience with average atomic mass, and check naturally occurring isotope ratios using the isotopes and atomic mass simulation. As you will learn, isotopes are important in nature and especially in human understanding of science and medicine. Let's consider just one natural stable isotope, OXYGEN18, which is noted in the table above and is referred to as one of the environmental isotopes. It is important in paleoclimatology, for example, because scientists can use the ratio between oxygen-18 and oxygen-16 in an ice core to determine the temperature of precipitation over time. Oxygen-18 was also critical to the discovery of metabolic pathways and the mechanisms of enzymes. Mildred Cohn pioneered the usage of these isotopes to act as tracers, so that researchers could follow their path through reactions and gain a better understanding of what is happening. One of her first discoveries provided insight into the phosphorylation of glucose that takes place in mitochondria. And the methods of using isotopes for this research contributed to entire fields of study. The occurrence and natural abundances of isotopes can be experimentally determined using an instrument called a mass spectrometer. Mass spectrometry, MS, is widely used in chemistry, forensics, medicine, environmental science, and many other fields to analyze and help identify the substances in a sample of material. In a typical mass spectrometer, figure 2.15, the sample is vaporized and exposed to a high-energy electron beam that causes the sample's atoms, or molecules, to become electrically charged, typically by losing one or more electrons. These cations then pass through a variable, electric or magnetic field that deflects each cation's path to an extent that depends on both its mass and charge, similar to how the path of a large steel ball rolling past a magnet is deflected to a lesser extent than that of a small steel ball. The ions are detected, and a plot of the relative number of ions generated versus their mass-to-charge ratios, a mass spectrum, is made. The height of each vertical feature or peak in a mass spectrum is proportional to the fraction of cations with the specified mass-to-charge ratio. Since its initial use during the development of modern atomic theory, MS has evolved to become a powerful tool for chemical analysis in a wide range of applications. The left diagram shows how a mass spectrometer works, which is primarily a large tube that bends downward at its midpoint. The sample enters on the left side of the tube. A heater heats the sample, causing it to vaporize. The sample is also hit with a beam of electrons as it is being vaporized. Charged particles from the sample, called ions, are then accelerated and pass between two magnets. The magnetic field deflects the lightest ions most. The deflection of the ions is measured by a detector located on the right side of the tube. The graph to the right of the spectrometer shows a mass spectrum of zirconium. The relative abundance, as a percentage from 0 to 100, is graphed on the y-axis, and the mass-to-charge ratio is graphed on the x-axis. The sample contains 5 different isomers of zirconium. Zr90, which has a mass-to-charge ratio of 90, is the most abundant isotope at about 51% relative abundance. Zr91 has a mass-to-charge ratio of 91 and a relative abundance of about 11%. Zr92 has a mass-to-charge ratio of 92 and a relative abundance of about 18%. Zr94 has a mass-to-charge ratio of 94 and a relative abundance of about 18%. Zr96, which has a mass-to-charge ratio of 96, is the least abundant zirconium isotope with a relative abundance of about 2%. Figure 2.15. Analysis of zirconium in a mass spectrometer produces a mass spectrum with peaks showing the different isotopes of Zr. Link to learning. See an animation that explains mass spectrometry. Watch this video from the Royal Society for Chemistry for a brief description of the rudiments of mass spectrometry. Learning objectives. By the end of this section, you will be able to symbolize the composition of molecules using molecular formulas and empirical formulas, represent the bonding arrangement of atoms within molecules using structural formulas. A molecular formula is a representation of a molecule that uses chemical symbols to indicate the types of atoms followed by subscripts to show the number of atoms of each type in the molecule. A subscript is used only when more than one atom of a given type is present. Molecular formulas are also used as abbreviations for the names of compounds. The structural formula for a compound gives the same information as its molecular formula, the types and numbers of atoms in the molecule, but also shows how the atoms are connected in the molecule. The structural formula for methane contains symbols for one C atom and 4 H atoms, indicating the number of atoms in the molecule, figure 2.16. The lines represent bonds that hold the atoms together. A chemical bond is an attraction between atoms or ions that holds them together in a molecule or a crystal. We will discuss chemical bonds and see how to predict the arrangement of atoms in a molecule later. For now, simply know that the lines are an indication of how the atoms are connected in a molecule. A ball and stick model shows the geometric arrangement of the atoms with atomic sizes not to scale, and a space-filling model shows the relative sizes of the atoms. Figure A shows CH subscript 4. Figure B shows a carbon atom that is bonded to 4 hydrogen atoms at right angles, one above, one to the left, one to the right, and one below. Figure C shows a 3D ball and stick model of the carbon atom bonded to 4 hydrogen atoms. Figure D shows a space-filling model of a carbon atom with hydrogen atoms partially embedded into the surface of the carbon atom. Figure 2.1, 6A methane molecule can be represented as A, a molecular formula, B, a structural formula, C, a ball and stick model, and D, a space-filling model. Carbon and hydrogen atoms are represented by black and white spheres, respectively. Although many elements consist of discrete, individual atoms, some exist as molecules made up of 2 or more atoms of the element chemically bonded together. For example, most samples of the elements hydrogen, oxygen, and nitrogen are composed of molecules that contain 2 atoms each, called diatomic molecules, and thus have the molecular formulas H2, O2, and N2 respectively. Other elements commonly found as diatomic molecules are fluorine, F2, chlorine, Cl2, bromine, bridge 2, and iodine, I2. The most common form of the element sulfur is composed of molecules that consist of 8 atoms of sulfur. Its molecular formula is S8. Figure 2.17. Figure A shows 8 sulfur atoms, symbolized with the letter S, that are bonded to each other to form an octagon. Figure B shows a 3D ball and stick model of the arrangement of the sulfur atoms. The shape is clearly not octagonal as it is represented in the structural formula. Figure C is a space-filling model that shows each sulfur atom is partially embedded into the sulfur atom it bonds with. Figure 2.17a molecule of sulfur is composed of 8 sulfur atoms and is therefore written as S8. It can be represented as A, a structural formula, B, a ball and stick model, and C, a space-filling model. Sulfur atoms are represented by yellow spheres. It is important to note that a subscript following a symbol and a number in front of a symbol do not represent the same thing. For example, H2 and 2H represent distinctly different species. H2 is a molecular formula. It represents a diatomic molecule of hydrogen, consisting of 2 atoms of the element that are chemically bonded together. The expression 2H, on the other hand, indicates 2 separate hydrogen atoms that are not combined as a unit. The expression 2H2 represents 2 molecules of diatomic hydrogen, figure 2.18. This figure shows 4 diagrams. The diagram for H shows a single white sphere and is labeled 1H atom. The diagram for 2H shows 2 white spheres that are not bonded together. It is labeled 2H atoms. The diagram for H subscript 2 shows 2 white spheres bonded together. It is labeled 1H subscript 2 molecule. The diagram for 2H subscript 2 shows 2 sets of bonded white spheres. It is labeled 2H subscript 2 molecules. Figure 2.18, the symbols H2H, H2, and 2H2 represent very different entities. Compounds are formed when 2 or more elements chemically combine, resulting in the formation of bonds. For example, hydrogen and oxygen can react to form water, and sodium and chlorine can react to form table salt. We sometimes describe the composition of these compounds with an empirical formula, which indicates the types of atoms present and the simplest whole number ratio of the number of atoms, or ions, in the compound. For example, titanium dioxide, used as pigment in white paint and in the thick white blocking type of sunscreen, has an empirical formula of TO2. This identifies the elements titanium, Ti, and oxygen O as the constituents of titanium dioxide, and indicates the presence of twice as many atoms of the element oxygen as atoms of the element titanium. Figure 2.19. Figure A shows a photo of a person applying suntan lotion to his or her lower leg. Figure B shows a 3D ball and stick model of the molecule titanium dioxide which involves a complicated interlocking of many titanium and oxygen atoms. The titanium atoms in the molecule are shown as silver spheres, and the oxygen atoms are shown as red spheres. There are twice as many oxygen atoms as titanium atoms in the molecule. Figure 2.19a. The white compound titanium dioxide provides effective protection from the sun. B. A crystal of titanium dioxide, TiO2, contains titanium and oxygen in a ratio of 1 to 2. The titanium atoms are gray and the oxygen atoms are red. Credit A. Modification of work by Osseous, Flicker. As discussed previously, we can describe a compound with a molecular formula in which the subscripts indicate the actual numbers of atoms of each element in a molecule of the compound. In many cases, the molecular formula of a substance is derived from experimental determination of both its empirical formula and its molecular mass, the sum of atomic masses for all atoms composing the molecule. For example, it can be determined experimentally that benzene contains two elements, carbon C and hydrogen H, and that for every carbon atom in benzene, there is one hydrogen atom. Thus, the empirical formula is CH. An experimental determination of the molecular mass reveals that a molecule of benzene contains 6 carbon atoms and 6 hydrogen atoms, so the molecular formula for benzene is C6H6. Figure 2.20. Figure A shows that benzene is composed of 6 carbons shaped like a hexagon. Every other bond between the carbon atoms is a double bond. Each carbon also has a single bonded hydrogen atom. Figure B shows a 3D ball-and-stick drawing of benzene. The 6 carbon atoms are black spheres, while the 6 hydrogen atoms are smaller, white spheres. Figure C is a space-filling model of benzene, which shows that most of the interior space is occupied by the carbon atoms. The hydrogen atoms are embedded in the outside surface of the carbon atoms. Figure D shows a small vial filled with benzene, which appears to be clear. Figure 2.20 benzene, C6H6, is produced during oil refining and has many industrial uses. A benzene molecule can be represented as A, a structural formula, B, a ball-and-stick model, and C, a space-filling model. D, benzene is a clear liquid. Credit D, modification of work by Sahar Atwa. If we know a compound's formula, we can easily determine the empirical formula. This is somewhat of an academic exercise. The reverse chronology is generally followed in actual practice. For example, the molecular formula for acetic acid, the component that gives vinegar its sharp taste, is C2H4O2. This formula indicates that a molecule of acetic acid, figure 2.21, contains 2 carbon atoms, 4 hydrogen atoms, and 2 oxygen atoms. The ratio of atoms is 2 to 4. 2, dividing by the lowest common denominator, 2, gives the simplest whole number ratio of atoms, 1. 2 to 1, so the empirical formula is CH2O. Note that a molecular formula is always a whole number multiple of an empirical formula. Figure A shows a jug of distilled white vinegar. Figure B shows a structural formula for acetic acid, which contains 2 carbon atoms connected by a single bond. The left carbon atom forms single bonds with 3 hydrogen atoms. The right carbon atom forms a double bond with an oxygen atom. The right carbon atom also forms a single bond with an oxygen atom. This oxygen forms a single bond with a hydrogen atom. Figure C shows a 3D ball-and-stick model of acetic acid. Figure 2.21a vinegar contains acetic acid, C2H4O2, which has an empirical formula of CH2O. It can be represented as B, a structural formula, and C as a ball-and-stick model. Credit A, modification of work by Homespot HQ/Flicker. Example 2.6. Empirical and molecular formulas. Molecules of glucose, blood sugar, contain 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. What are the molecular and empirical formulas of glucose? Solution. The molecular formula is C6H12O6 because one molecule actually contains 6C, 12H, and 6O atoms. The simplest whole number ratio of CH to O atoms in glucose is 1 to 2. 1 So the empirical formula is CH2O. Check your learning. A molecule of metaldehyde, a pesticide used for snails and slugs, contains 8 carbon atoms, 16 hydrogen atoms, and 4 oxygen atoms. What are the molecular and empirical formulas of metaldehyde? Answer: molecular formula C8 hydrogen oxide, empirical formula C2H4O. Link to learning. You can explore molecule building using an online simulation. Portrait of a chemist. Paula Hammond. You've learned about the evolution of atomic theory, and you've started to explore different chemical structures. These structures result in molecules attracting or repelling each other, or help them arrange into our cell membranes, or lead them to either spread into thin films or clump into solid masses. What do these structures mean to scientists and to us? Essentially everything. It's the structure and makeup of a molecule on a virus surface that allows it to attach to one of our cells, and it's the structure and makeup of antibodies, substances created by our immune system, that block that attachment. Chlorophyll's structure enables it to use the sun's energy to make glucose. Chemists and chemical engineers don't simply observe and understand these structures. They can create new ones. A portrait of Paula Hammond. Figure 2.22, Paula Hammond pioneered new techniques to precisely formulate chemical structures. Hammond's work applies to cancer treatments, wound healing, cataract medicine, and fuel cells. Widely recognized as a leader in the field, she has won numerous awards and has been elected to various prestigious positions and fellowships by her peers and the U.S. government. She chairs the Chemical Engineering Department at MIT, which is usually ranked as one of the best engineering and science institutions in the world. Credit: modification of work by the White House. Paula Hammond does exactly that to solve challenging problems ranging from cancer to energy consumption. She is the chair of the Department of Chemical Engineering at Massachusetts Institute of Technology and leads a research team focused on assembling unique molecular structures. They have created cancer drug carriers, nanoparticle-sized coatings that enable medicines to travel into tumors without being affected by its defenses, that can deliver pharmaceuticals directly into cancerous tumors. They build these stealth molecules layer by layer. Using certain properties of electricity and chemical behavior, they can tune the coatings to address particular cancers and other variables. This precision approach is necessary to treat cancers more effectively and with less harm to the patient. The company Hammond founded uses similar technology to release medication into cataract patients' eyes, as well as to improve wound healing. While Hammond's research team is composed of established and leading experts such as herself, students certainly play a role. College research labs are typically full of PhD, graduate, and even undergraduate students who participate in the work. And thus, chemists and chemical engineers who use their knowledge to solve problems are also supporting the next generation of creators and problem solvers. It is important to be aware that it may be possible for the same atoms to be arranged in different ways. Compounds with the same molecular formula may have different atom-to-atom bonding and therefore different structures. For example, could there be another compound with the same formula as acetic acid, C2H4O2? And if so, what would be the structure of its molecules? If you predict that another compound with the formula C2H4O2 could exist, then you demonstrated good chemical insight and are correct. 2 C atoms, 4 H atoms, and 2 O atoms can also be arranged to form a methyl formate, which is used in manufacturing, as an insecticide, and for quick-drying finishes. Methyl formate molecules have one of the oxygen atoms between the 2 carbon atoms, differing from the arrangement in acetic acid molecules. Acetic acid and methyl formate are examples of isomers, compounds with the same chemical formula but different molecular structures, figure 2.23. Note that this small difference in the arrangement of the atoms has a major effect on their respective chemical properties. You would certainly not want to use a solution of methyl formate as a substitute for a solution of acetic acid, vinegar, when you make salad dressing. Figure A shows a structural diagram of acetic acid, C subscript 2 H subscript 4O subscript 2. Acetic acid contains 2 carbon atoms connected by a single bond. The left carbon atom forms single bonds with 3 hydrogen atoms. The carbon on the right forms a double bond with an oxygen atom. The right carbon atom also forms a single bond to an oxygen atom, which forms a single bond with a hydrogen atom. Figure B shows a structural diagram of methyl formate C subscript 2 H subscript 4O subscript 2. This molecule contains a carbon atom which forms single bonds with 3 hydrogen atoms and a single bond with an oxygen atom. The oxygen atom forms a single bond with another carbon atom, which forms a double bond with another oxygen atom and a single bond with a hydrogen atom. Figure 2.23 molecules of A acetic acid and methyl formate B are structural isomers. They have the same formula, C2H4O2, but different structures, and therefore different chemical properties. Many types of isomers exist. Figure 2.24, acetic acid and methyl formate are structural isomers, compounds in which the molecules differ in how the atoms are connected to each other. There are also various types of spatial isomers, in which the relative orientations of the atoms in space can be different. For example, the compound carvone found in caraway seeds, spearmint, and mandarin orange peels consists of 2 isomers that are mirror images of each other. S plus carvone smells like caraway, and R minus carvone smells like spearmint. The top left portion of this 2-row, 4-column figure shows a structural diagram of positive carvone C subscript 10H subscript 14O. This molecule has a carbon atom which forms a double bond with a CH subscript 2 group and a CH subscript 3 group. The carbon atom also forms a single bond with another carbon atom which is part of a ring. This carbon atom, being part of the ring, forms single bonds with a hydrogen atom, a CH subscript 2 group, and a CH subscript 2 group. The first CH subscript 2 group forms a single bond with CH, which forms a double bond with a carbon atom. This carbon atom forms a single bond with a CH subscript 3 group. The carbon atom forming part of the ring forms a single bond with a carbon atom, which forms a double bond with an oxygen atom, and a single bond with a CH subscript 2 group to complete the ring. Below the structural diagram of carvone is a photo of caraway seeds. Column 2 contains identical ball and stick representations of the structural diagram in the top left position. The top right portions of these images each contains the letter S, and there is an arrow pointing downward from the top image to the bottom image. Columns 3 and 4 are representations of negative carvone. The top row in column 3 depicts a mirrored image of the ball and stick structure to its left, reflected across the y-axis. There is a downward pointing arrow to the image below, which is the same structure rotated counterclockwise 180 degrees. Both images in column 3 have an R in the top right corner. The image in the first row of column 4 is the same as the Lewis structure in the first row of column 1, reflected across the y-axis. Below this negative carvone structural diagram is a photo of spearmint leaves. Figure 2.24. Molecules of carvone are spatial isomers. They only differ in the relative orientations of the atoms in space. Credit bottom left, modification of work by Miansari 66, Wikimedia Commons. Credit bottom right, modification of work by Forrest and Kim Starr. Link to learning. Select this link to view an explanation of isomers, spatial isomers, and why they have different smells. Select the video titled Mirror Molecule Carvone. Learning objectives. By the end of this section, you will be able to state the periodic law and explain the organization of elements in the periodic table. Predict the general properties of elements based on their location within the periodic table. Identify metals, nonmetals, and metalloids by their properties and/or location on the periodic table. As early chemists worked to purify ores and discovered more elements, they realized that various elements could be grouped together by their similar chemical behaviors. One such grouping includes lithium Li, sodium Na, and potassium K. These elements all are shiny, conduct heat and electricity well, and have similar chemical properties. A second grouping includes calcium Ca, strontium Senior, and barium Ba, which also are shiny, good conductors of heat and electricity, and have chemical properties in common. However, the specific properties of these two groupings are notably different from each other. For example, Li, Na, and K are much more reactive than are Ca Senior and Ba. Li, Na, and K form compounds with oxygen in a ratio of 2 of their atoms to 1 oxygen atom. whereas Ca senior and Ba form compounds with one of their atoms to one oxygen atom. Fluorine F, chlorine Cl, bromine bridge, and iodine I also exhibit similar properties to each other, but these properties are drastically different from those of any of the elements above. Dmitry Mendeleev in Russia, 1869, and Lothar Meyer in Germany, 1870, independently recognized that there was a periodic relationship among the properties of the elements known at that time. Both published tables with the elements arranged according to increasing atomic mass. But Mendeleev went one step further than Meyer. He used his table to predict the existence of elements that would have the properties similar to aluminum and silicon, but were yet unknown. The discoveries of gallium, 1875, and germanium, 1886, provided great support for Mendeleev's work. Although Mendeleev and Meyer had a long dispute over priority, Mendeleev's contributions to the development of the periodic table are now more widely recognized. Figure 2.25. Figure A shows a photograph of Dmitry Mendeleev. Figure B shows the first periodic table developed by Mendeleev, which had 8 groups and 12 periods. In the first group, R superscript plus sign 0 is the following information: H equals 1, Li equals 7, Na equals 23, K equals 39, Cu equals 63, Rb equals 85, Ag equals 108, Ca equals 183, Au equals 199. Note that each of these entries corresponds to one of the 12 periods respectively. The second group, R0, contains the following information: not entry for period 1. BO equals 9, 4, Mg equals 24, Ca equals 40, Zn equals 65, Sr equals 87, Cd equals 112, Ba equals 187, Hg equals 200. Note the ACH of these entries corresponds to one of the 12 periods respectively. Group 3, R superscript 10 superscript 9 contains the information: no entry for period 1. B equals 11, Al equals 27, 8, equals 44, equals 68, Yt equals 88, In equals 113, Di equals 138, Er equals 178, Tl equals 204. Note that each of these entries corresponds to one of the 12 periods respectively. Group 4, Rh superscript 4, R0 superscript 8, contains the following information: no entry for period 1. C equals 12, Bi equals 28, Ti equals 48, equals 72, Zr equals 90, Sn equals 118, Co equals 140, La equals 180, Pb equals 207, Th equals 231. Note that each of these entries corresponds to one of the 12 periods respectively. Group 5, Rh superscript 2, R superscript 20 superscript 5, contains the following information: no entry for period 1, N equals 14, P equals 31, V equals 51, As equals 75, Nb equals 94, Sb equals 122, Ta equals 182, Bl equals 208. Note that each of these entries corresponds to one of the 12 periods respectively. Group 6, Rh superscript 2, R0 superscript 3, contains the following information: no entry for period 1. O equals 16, S equals 32, Cr equals 52, So equals 78, Mo equals 96, To equals 125, W equals 184, U equals 240. Note that each of these entries corresponds to one of the 12 periods respectively. Group 7, RHR superscript plus Sing 0 superscript 7, contains the following information: no entry for period 1. F equals 19, Cl equals 35, 5, Mn equals 55, Br equals 80, equals 100, J equals 127, J equals 127, Note that each of these entries corresponds to one of the 12 periods respectively. Group 8, R0 superscript 4, contains the following information. No entry for periods 1, 2, 3 in period 4. FO equals 56, CO equals 59, NI equals 59, CU equals 63. No entry for period 5 in period 6. RU equals 104, RH equals 104, PD equals 108. No entries for period 7, 8, or 9 in period 10. OS equals 195, IR. Figure 2.25a, Dmitry Mendeleev, is widely credited with creating B, the first periodic table of the elements. Credit A, modification of work by Sergei Lachinov. Credit B, modification of work by Denfiatrade Ankan, Wikimedia Commons. By the 20th century, it became apparent that the periodic relationship involved atomic numbers rather than atomic masses. The modern statement of this relationship, the periodic law, is as follows. The properties of the elements are periodic functions of their atomic numbers. A modern periodic table arranges the elements in increasing order of their atomic numbers and groups atoms with similar properties in the same vertical column, Figure 2.26. Each box represents an element and contains its atomic number, symbol, average atomic mass, and sometimes name. The elements are arranged in 7 horizontal rows, called periods or series, and 18 vertical columns, called groups. Groups are labeled at the top of each column. In the United States, the labels traditionally were numerals with capital letters. However, IUPAC recommends that the numbers 1 through 18 be used, and these labels are more common. For the table to fit on a single page, parts of 2 of the rows, a total of 14 columns, are usually written below the main body of the table. Figure 2.26 elements in the periodic table are organized according to their properties. Even after the periodic nature of elements and the table itself were widely accepted, gaps remained. Mendeleev had predicted, and others including Henry Moseley had later confirmed, that there should be elements below manganese in group 7. German chemists Ida Take and Walter Noddack set out to find the elements, a quest being pursued by scientists around the world. Their method was unique in that they did not only consider the properties of manganese, but also the elements horizontally adjacent to the missing elements 43 and 75 on the table. Thus, by investigating ores containing minerals of ruthenium, Ru, tungsten W, osmium Os, and so on, they were able to identify naturally occurring elements that help complete the table. Rhenium, one of their discoveries, was one of the last natural elements to be discovered and is the last stable element to be discovered. Francium, the last natural element to be discovered, was identified by Marguerite Perret in 1939. Many elements differ dramatically in their chemical and physical properties, but some elements are similar in their behaviors. For example, many elements appear shiny, are malleable, able to be deformed without breaking, and ductile, can be drawn into wires, and conduct heat and electricity well. Other elements are not shiny, malleable, or ductile, and are poor conductors of heat and electricity. We can sort the elements into large classes with common properties. Metals, elements that are shiny, malleable, good conductors of heat and electricity, shaded yellow. Nonmetals, elements that appear dull, poor conductors of heat and electricity, shaded green. And metalloids, elements that conduct heat and electricity moderately well, and possess some properties of metals and some properties of nonmetals, shaded purple. The elements can also be classified into the main group elements, or representative elements, in the columns labeled 1, 2, and 13 to 18. The transition metals in the columns labeled 3 to 122, and intertransition metals in the 2 rows at the bottom of the table. The top row elements are called lanthanides, and the bottom row elements are actinides. Figure 2.27. The elements can be subdivided further by more specific properties, such as the composition of the compounds they form. For example, the elements in group 1, the first column, form compounds that consist of 1 atom of the element and 1 atom of hydrogen. These elements, except hydrogen, are known as alkali metals, and they all have similar chemical properties. The elements in group 2, the second column, form compounds consisting of 1 atom of the element and 2 atoms of hydrogen. These are called alkaline earth metals, with similar properties among members of that group. Other groups with specific names are the pnictogens, group 15, chalcogens, group 16, halogens, group 17, and the noble gases, group 18, also known as inert gases. The groups can also be referred to by the first element of the group. For example, the chalcogens can be called the oxygen group or oxygen family. Hydrogen is a unique, nonmetallic element with properties similar to both group 1 and group 17 elements. For that reason, hydrogen may be shown at the top of both groups or by itself. This diagram combines the groups and periods of the periodic table based on their similar properties. Group 1 contains the alkali metals. Group 2 contains the earth alkaline metals. Group 15 contains the pnictogens. Group 16 contains the chalcogens. Group 17 contains the halogens, and Group 18 contains the noble gases. The main group elements consist of groups 1, 2, and 12 through 18. Therefore, most of the transition metals, which are contained in groups 3 through 11, are not main group elements. The lanthanides and actinides are called out at the bottom of the periodic table. Figure 2.27. The periodic table organizes elements with similar properties into groups. Link to learning. Click on this link for an interactive periodic table, which you can use to explore the properties of the elements. Includes podcasts and videos of each element. You may also want to try this one that shows photos of all the elements. Example 2.7. Naming groups of elements. Atoms of each of the following elements are essential for life. Give the group name for the following elements. A. Chlorine. B. Calcium. C. Sodium. D. Sulfur. Solution. The family names are as follows. A. Halogen. B. Selenium. C. Alkaline earth metal. D. Chalcogen. A. Noble gas. B. Chalcogen. C. Alkaline earth metal. D. Alkali metal. As you will learn in your further study of chemistry, elements and groups often behave in a somewhat similar manner. This is partly due to the number of electrons in their outer shell and their similar readiness to bond. These shared properties can have far-ranging implications in nature, science, and medicine. For example, when Gertrude Elion and George Hitchens were investigating ways to interrupt cell and virus replication to fight diseases, they utilized the similarity between sulfur and oxygen, both in group 16, and their capacity to bond in similar ways. Elion focused on purines, which are key components of DNA and which contain oxygen. She found that by introducing sulfur-based compounds called purine analogs that mimic the structure of purines, molecules within DNA would bond to the analogs rather than the regular DNA purine. With the normal DNA bonding and structure altered, Elion successfully interrupted cell replication. At its core, the strategy worked because of the similarity between sulfur and oxygen. Her discovery led directly to important treatments for leukemia. Overall, Elion's work with George Hitchens not only led to more treatments but also changed the entire methodology of drug development. By using specific elements and compounds to target specific aspects of tumor cells, viruses, and bacteria, they laid the groundwork for many of today's most common and important medicines, used to help millions of people each year. They were awarded the Nobel Prize in 1988. In studying the periodic table, you might have noticed something about the atomic masses of some of the elements. Element 43, technetium, element 61, promethium, and most of the elements with atomic number 84, polonium and higher, have their atomic mass given in square brackets. This is done for elements that consist entirely of unstable, radioactive isotopes. You will learn more about radioactivity in the nuclear chemistry chapter. An average atomic weight cannot be determined for these elements because their radioisotopes may vary significantly in relative abundance, depending on the source, or may not even exist in nature. The number in square brackets is the atomic mass number and approximate atomic mass of the most stable isotope of that element. Learning objectives. By the end of this section, you will be able to define ionic and molecular covalent compounds. Predict the type of compound formed from elements based on their location within the periodic table. Determine formulas for simple ionic compounds. In ordinary chemical reactions, the nucleus of each atom, and thus the identity of the element, remains unchanged. Electrons, however, can be added to atoms by transfer from other atoms, lost by transfer to other atoms, or shared with other atoms. The transfer and sharing of electrons among atoms govern the chemistry of the elements. During the formation of some compounds, atoms gain or lose electrons, and form electrically charged particles called ions. Figure 2.28. Figure A shows a sodium atom, Na, which has a nucleus containing 11 protons and 12 neutrons. The atom surrounding electron cloud contains 11 electrons. Figure B shows a sodium ion, N, a superscript plus sign. Its nucleus contains 11 protons and 12 neutrons. The ion's electron cloud contains 10 electrons and is smaller than that of the sodium atom in Figure A. Figure 2.28a, a sodium atom, Na, has equal numbers of protons and electrons, 11, and is uncharged. B, a sodium cation, Na+, has lost an electron, so it has one more proton, 11, than electrons, 10, giving it an overall positive charge, signified by a superscripted plus sign. You can use the periodic table to predict whether an atom will form an anion or a cation, and you can often predict the charge of the resulting ion. Atoms of many main group metals lose enough electrons to leave them with the same number of electrons as an atom of the preceding noble gas. To illustrate, an atom of an alkali metal, group 1, loses 1 electron and forms a cation with a 1+ charge. An alkaline earth metal, group 2, loses 2 electrons and forms a cation with a 2+ charge, and so on. For example, a neutral calcium atom with 20 protons and 20 electrons readily loses 2 electrons. This results in a cation with 20 protons, 18 electrons, and a 2+ charge. It has the same number of electrons as atoms of the preceding noble gas, argon, and is symbolized Ca2+. The name of a metal ion is the same as the name of the metal atom from which it forms, so Ca2+ is called a calcium ion. When atoms of non-metal elements form ions, they generally gain enough electrons to give them the same number of electrons as an atom of the next noble gas in the periodic table. Atoms of group 17 gain 1 electron and form anions with a 1- charge. Atoms of group 16 gain 2 electrons and form ions with a 2- charge, and so on. For example, the neutral bromine atom with 35 protons and 35 electrons can gain 1 electron to provide it with 36 electrons. This results in an anion with 35 protons, 36 electrons, and a 1- charge. It has the same number of electrons as atoms of the next noble gas, krypton, and is symbolized Bridge-. A discussion of the theory supporting the favored status of noble gas electron numbers reflected in these predictive rules for ion formation is provided in a later chapter of this text. Note the usefulness of the periodic table in predicting likely ion formation and charge, Figure 2.29. Moving from the far left to the right on the periodic table, main group elements tend to form cations with a charge equal to the group number. That is, Group 1 elements form 1+ ions, Group 2 elements form 2+ ions, and so on. Moving from the far right to the left on the periodic table, elements often form anions with a negative charge equal to the number of groups moved left from the noble gases. For example, Group 17 elements, one group left of the noble gases, form 1- ions. Group 16 elements, 2 groups left, form 2- ions, and so on. This trend can be used as a guide in many cases, but its predictive value decreases when moving toward the center of the periodic table. In fact, transition metals and some other metals often exhibit variable charges that are not predictable by their location in the table. For example, copper can form ions with a 1+ or 2+ charge, and iron can form ions with a 2+ or 3+ charge. Figure 2.29. Some elements exhibit a regular pattern of ionic charge when they form ions. Example 2.8. Composition of ions. An ion found in some compounds used as antiperspirants contains 13 protons and 10 electrons. What is its symbol? Solution. Because the number of protons remains unchanged when an atom forms an ion, the atomic number of the element must be 13. Knowing this lets us use the periodic table to identify the element as Al, aluminum. The Al atom has lost 3 electrons and thus has 3 more positive charges, 13, than it has electrons, 10. This is the aluminum cation, Al 3+. Check your learning. Give the symbol and name for the ion with 34 protons and 36 electrons. Answer. Se2-, the selenide ion. Example 2.9. Formation of ions. Magnesium and nitrogen react to form an ionic compound. Predict which forms an anion, which forms a cation, and the charges of each ion. Write the symbol for each ion and name them. Solution. Magnesium's position in the periodic table, group 2, tells us that it is a metal. Metals form positive ions, cations. A magnesium atom must lose 2 electrons to have the same number of electrons as an atom of the previous noble gas, neon. Thus, a magnesium atom will form a cation with 2 fewer electrons than protons and a charge of 2+. The symbol for the ion is Mg2+, and it is called a magnesium ion. Nitrogen's position in the periodic table, group 15, reveals that it is a nonmetal. Nonmetals form negative ions, anions. A nitrogen atom must gain 3 electrons to have the same number of electrons as an atom of the following noble gas, neon. Thus, a nitrogen atom will form an anion with 3 more electrons than protons and a charge of 3-. The symbol for the ion is N3-, and it is called a nitride ion. Check your learning. Aluminum and carbon react to form an ionic compound. Predict which forms an anion, which forms a cation, and the charges of each ion. Write the symbol for each ion and name them. Answer. Al will form a cation with a charge of 3+, Al3+, an aluminum ion. Carbon will form an anion with a charge of 4-, C4-, a carbide ion. The ions that we have discussed so far are called monatomic ions, that is, they are ions formed from only one atom. We also find many polyatomic ions. These ions, which act as discrete units, are electrically charged molecules, a group of bonded atoms with an overall charge. Some of the more important polyatomic ions are listed in Table 2.5. Oxyanions are polyatomic ions that contain 1 or more oxygen atoms. At this point in your study of chemistry, you should memorize the names, formulas, and charges of the most common polyatomic ions. Because you will use them repeatedly, they will soon become familiar. Table 2.5. Note that there is a system for naming some polyatomic ions. Ate and ite are suffixes designating polyatomic ions containing more or fewer oxygen atoms. Per, short for hyper and hypo, meaning under, are prefixes meaning more oxygen atoms than ate and fewer oxygen atoms than ite, respectively. For example, perchlorate is ClO4-, chlorate is ClO3-, chlorite is ClO2-, and hypochlorite is ClO-. Unfortunately, the number of oxygen atoms corresponding to a given suffix or prefix is not consistent. For example, nitrate is NO3-, while sulfate is SO42-. This will be covered in more detail in the next module on nomenclature. The nature of the attractive forces that hold atoms or ions together within a compound is the basis for classifying chemical bonding. When electrons are transferred in ions form, ionic bonds result. Ionic bonds are electrostatic forces of attraction, that is, the attractive forces experienced between objects of opposite electrical charge, in this case cations and anions. When electrons are shared and molecules form, covalent bonds result. Covalent bonds are the attractive forces between the positively charged nuclei of the bonded atoms and 1 or more pairs of electrons that are located between the atoms. Compounds are classified as ionic or molecular, covalent, on the basis of the bonds present in them. Ionic compounds. When an element composed of atoms that readily lose electrons, a metal, reacts with an element composed of atoms that readily gain electrons, a nonmetal, a transfer of electrons usually occurs, producing ions. The compound formed by this transfer is stabilized by the electrostatic attractions, ionic bonds, between the ions of opposite charge present in the compound. For example, when each sodium atom in a sample of sodium metal, group 1, gives up 1 electron to form a sodium cation, Na+, and each chlorine atom in a sample of chlorine gas, group 17, accepts one electron to form a chloride anion, Cl-. The resulting compound, sodium chloride, is composed of sodium ions and chloride ions in the ratio of 1 Na+ ion for each Cl- ion. Similarly, each calcium atom, group 2, can give up 2 electrons and transfer 1 to each of 2 chlorine atoms to form CaCl2, which is composed of Ca2+ and Cl- ions in the ratio of 1 Ca2+ ion to 2 Cl- ions. A compound that contains ions and is held together by ionic bonds is called an ionic compound. The periodic table can help us recognize many of the compounds that are ionic. When a metal is combined with one or more nonmetals, the compound is usually ionic. This guideline works well for predicting ionic compound formation for most of the compounds typically encountered in an introductory chemistry course. However, it is not always true. For example, aluminum chloride, AlCl3, is not ionic. You can often recognize ionic compounds because of their properties. Ionic compounds are solids that typically melt at high temperatures and boil at even higher temperatures. For example, sodium chloride melts at 801 degrees Celsius and boils at 1413 degrees Celsius. As a comparison, the molecular compound water melts at 0 degrees Celsius and boils at 100 degrees Celsius. In solid form, an ionic compound is not electrically conductive because its ions are unable to flow. Electricity is the flow of charged particles. When molten, however, it can conduct electricity because its ions are able to move freely through the liquid. Figure 2.30. This figure shows 3 photos connected by right-facing arrows. The first shows a light bulb as part of a complex lab equipment setup. The light bulb is not lit. The second photo shows a substances being heated or set on fire. The third shows the light bulb again, which is lit. Figure 2.30. Sodium chloride melts at 801 degrees Celsius and conducts electricity when molten. Credit: Modification of work by Mark Blazer and Matt Evans. Link to learning. Watch this video to see a mixture of salts melt and conduct electricity. In every ionic compound, the total number of positive charges of the cations equals the total number of negative charges of the anions. Thus, ionic compounds are electrically neutral overall, even though they contain positive and negative ions. We can use this observation to help us write the formula of an ionic compound. The formula of an ionic compound must have a ratio of ions such that the numbers of positive and negative charges are equal. Example 2.10. Predicting the formula of an ionic compound. The gemstone sapphire, figure 2.31, is mostly a compound of aluminum and oxygen that contains aluminum cations, Al3+, and oxygen anions, O2-. What is the formula of this compound? This is a photograph of a ring with a sapphire set in it. Figure 2.3.1. Although pure aluminum oxide is colorless, trace amounts of iron and titanium give blue sapphire its characteristic color. Credit: Modification of work by Stanislav Doronenko. Solution: because the ionic compound must be electrically neutral, it must have the same number of positive and negative charges. 2 aluminum ions, each with a charge of 3+, would give us 6 positive charges, and 3 oxide ions, each with a charge of 2-, would give us 6 negative charges. The formula would be aluminium oxide. Check your learning. Predict the formula of the ionic compound formed between the sodium cation Na+ and the sulfide anion S2-. Answer: Na2S. Many ionic compounds contain polyatomic ions, table 2.5, as the cation, the anion, or both. As with simple ionic compounds, these compounds must also be electrically neutral, so their formulas can be predicted by treating the polyatomic ions as discrete units. We use parentheses in a formula to indicate a group of atoms that behave as a unit. For example, the formula for calcium phosphate, one of the minerals in our bones, is calcium phosphate. This formula indicates that there are 3 calcium ions, Ca2+, for every 2 phosphate, PO43-, groups. The PO43- groups are discrete units, each consisting of 1 phosphorus atom and 4 oxygen atoms, and having an overall charge of 3-. The compound is electrically neutral, and its formula shows a total count of 3 Ca, 2 P, and 8 O atoms. Example 2.11. Predicting the formula of a compound with a polyatomic anion. Baking powder contains calcium dihydrogen phosphate, an ionic compound composed of the ions Ca2+ and H2PO4-. What is the formula of this compound? Solution. The positive and negative charges must balance, and this ionic compound must be electrically neutral. Thus, we must have two negative charges to balance the 2+ charge of the calcium ion. This requires a ratio of 1 Ca2+ ion to 2 H2PO4- ions. We designate this by enclosing the formula for the dihydrogen phosphate ion in parentheses and adding a subscript 2. The formula is CaH2PO4 2. Check your learning. Predict the formula of the ionic compound formed between the lithium ion and the peroxide ion O22-. Hint: use the periodic table to predict the sign and the charge on the lithium ion. Answer: Li2O2. Because an ionic compound is not made up of single discrete molecules, it may not be properly symbolized using a molecular formula. Instead, ionic compounds must be symbolized by a formula indicating the relative numbers of its constituent ions. For compounds containing only monatomic ions, such as sodium chloride, and for many compounds containing polyatomic ions, such as calcium sulfate, these formulas are just the empirical formulas introduced earlier in this chapter. However, the formulas for some ionic compounds containing polyatomic ions are not empirical formulas. For example, the ionic compound sodium oxalate is comprised of Na+ and C2O42- ions combined in a 2:1 ratio, and its formula is written as sodium oxalate. The subscripts in this formula are not the smallest possible whole numbers, as each can be divided by 2 to yield the empirical formula, NaCO2. This is not the accepted formula for sodium oxalate, however, as it does not accurately represent the compound's polyatomic anion C2O42-. Molecular compounds. Many compounds do not contain ions, but instead consist solely of discrete neutral molecules. These molecular compounds, covalent compounds, result when atoms share rather than transfer, gain or lose, electrons. Covalent bonding is an important and extensive concept in chemistry, and it will be treated in considerable detail in a later chapter of this text. We can often identify molecular compounds on the basis of their physical properties. Under normal conditions, molecular compounds often exist as gases, low-boiling liquids, and low-melting solids, although many important exceptions exist. Whereas ionic compounds are usually formed when a metal and a nonmetal combine, covalent compounds are usually formed by a combination of nonmetals. Thus, the periodic table can help us recognize many of the compounds that are covalent. While we can use the positions of a compound's elements in the periodic table to predict whether it is ionic or covalent at this point in our study of chemistry, you should be aware that this is a very simplistic approach that does not account for a number of interesting exceptions. Shades of gray exist between ionic and molecular compounds, and you'll learn more about those later. Example 2.12. Predicting the type of bonding in compounds. Predict whether the following compounds are ionic or molecular. A. Ki, the compound used as a source of iodine in table salt. B. H2O2, the bleach and disinfectant hydrogen peroxide. C. CHCl3, the anesthetic chloroform. D. Li2CO3, a source of lithium in antidepressants. Solution. A. Potassium group 1 is a metal, and B. Hydrogen group 1 is a nonmetal, and oxygen group 16 is a nonmetal. H2O2 is predicted to be molecular. C. Carbon group 14 is a nonmetal, hydrogen group 1 is a nonmetal, and chlorine group 17 is a nonmetal. CHCl3 is predicted to be molecular. D. Lithium group 1 is a metal, and carbonate is a polyatomic ion. Li2CO3 is predicted to be ionic. Check your learning. Using the periodic table, predict whether the following compounds are ionic or covalent. A. SO2. B. CaF2. Cn2H4. D. Aluminium sulfate. Answer: A. Molecular, B. Ionic, C. Molecular, D. Ionic. Learning objectives. By the end of this section, you will be able to derive names for common types of inorganic compounds using a systematic approach. Nomenclature, a collection of rules for naming things, is important in science and in many other situations. This module describes an approach that is used to name simple ionic and molecular compounds, such as sodium chloride, calcium carbonate, and N2O4. The simplest of these are binary compounds, those containing only two elements. But we will also consider how to name ionic compounds containing polyatomic ions, and one specific, very important class of compounds known as acids. Subsequent chapters in this text will focus on these compounds in great detail. We will limit our attention here to inorganic compounds, compounds that are composed principally of elements other than carbon, and will follow the nomenclature guidelines proposed by IUPAC. The rules for organic compounds in which carbon is the principal element will be treated in a later chapter on organic chemistry. Ionic compounds. To name an inorganic compound, we need to consider the answers to several questions. First, is the compound ionic or molecular? If the compound is ionic, does the metal form ions of only one type, fixed charge, or more than one type, variable charge? Are the ions monatomic or polyatomic? If the compound is molecular, does it contain hydrogen? If so, does it also contain oxygen? From the answers we derive, we place the compound in an appropriate category and then name it accordingly. Compounds containing only monatomic ions. The name of a binary compound containing monatomic ions consists of the name of the cation, the name of the metal, followed by the name of the anion, the name of the nonmetallic element with its ending replaced by the suffix -id. Some examples are given in Table 2.6. Names of some ionic compounds. Sodium chloride, sodium chloride, sodium oxide, sodium oxide. KBr, potassium bromide, CDS, cadmium sulfide. CaI2, calcium iodide, magnesium nitride, magnesium nitride. CSF, cesium fluoride, Ca3P2, calcium phosphide. Lithium chloride, Al4, C3, aluminum carbide. Table 2.6. Compounds containing polyatomic ions. Compounds containing polyatomic ions are named similarly to those containing only monatomic ions, i.e., by naming first the cation and then the anion. Examples are shown in Table 2.7. Names of some polyatomic ionic compounds. KC2H3O2, potassium acetate ammonium chloride, ammonium chloride. NaHCO3, sodium bicarbonate, calcium sulfate, calcium sulfate. Aluminium carbonate 3, aluminum carbonate, magnesium phosphate, magnesium phosphate. Table 2.7. Chemistry in everyday life. Ionic compounds in your cabinets. Every day you encounter and use a large number of ionic compounds. Some of these compounds, where they are found, and what they are used for, are listed in Table 2.8. Look at the label or ingredients list on the various products that you use during the next few days, and see if you run into any of those in this table, or find other ionic compounds that you could now name or write as a formula. Everyday ionic compounds. Ionic compound use. Sodium chloride, ordinary table salt. Ki, potassium iodide added to, quote, iodized salt for thyroid health. NaF, sodium fluoride ingredient in toothpaste. NaHCO3, sodium bicarbonate baking soda, used in cooking and as antacid. Na2CO3, sodium carbonate washing soda, used in cleaning agents. NaOCl, sodium hypochlorite, active ingredient in household bleach. Casio, calcium carbonate ingredient in antacids. Magnesium hydroxide 2, magnesium hydroxide ingredient in antacids. AlOH3, aluminum hydroxide ingredient in antacids. NaOH, sodium hydroxide lye, used as drain cleaner. K3PO4, potassium phosphate food additive, many purposes. Magnesium sulfate added to purified water. Na2HPO4, sodium hydrogen phosphate anti-caking agent used in powdered products. Nt2SO3, sodium sulfite preservative. Table 2.8. Compounds containing a metal ion with a variable charge. Most of the transition metals and some main group metals can form two or more cations with different charges. Compounds of these metals with nonmetals are named with the same method as compounds in the first category, except the charge of the metal ion is specified by a Roman numeral in parentheses after the name of the metal. The charge of the metal ion is determined from the formula of the compound and the charge of the anion. For example, consider binary ionic compounds of iron and chlorine. Iron typically exhibits a charge of either 2+ or 3+, see Figure 2.29, and the two corresponding compound formulas are iron 2 chloride and iron 3 chloride. The simplest name, iron chloride, will in this case be ambiguous, as it does not distinguish between these two compounds. In cases like this, the charge of the metal ion is included as a Roman numeral in parentheses immediately following the metal name. These two compounds are then unambiguously named iron 2 chloride and iron 3 chloride respectively. Other examples are provided in Table 2.9. Some ionic compounds with variably charged metal ions. Compound name: iron 2 chloride, iron 2 chloride. Iron 3 chloride, iron 3 chloride. Hg2O mercury, I, oxide. HgO mercury 2 oxide. SnF2 tin 2 fluoride. SnF4 tin IV fluoride. Table 2.9. Out-of-date nomenclature used the suffixes IC and As to designate metals with higher and lower charges respectively. Iron 3 chloride, FeCl3, was previously called ferric chloride, and iron 2 chloride, FeCl2, was known as ferrous chloride. Though this naming convention has been largely abandoned by the scientific community, it remains in use by some segments of industry. For example, you may see the word stannous fluoride on a tube of toothpaste. This represents the formula SnF2, which is more properly named tin 2 fluoride. The other fluoride of tin is SnF4, which was previously called stannic fluoride, but is now named tin IV fluoride. Ionic hydrates. Ionic compounds that contain water molecules as integral components of their crystals are called hydrates. The name for an ionic hydrate is derived by adding a term to the name for the anhydrous, meaning not hydrated, compound that indicates the number of water molecules associated with each formula unit of the compound. The added word begins with a Greek prefix denoting the number of water molecules, see Table 2.10, and ends with hydrate. For example, the anhydrous compound copper 2 sulfate also exists as a hydrate containing 5 water molecules and named copper 2 sulfate pentahydrate. Washing soda is the common name for a hydrate of sodium carbonate containing 10 water molecules. The systematic name is sodium carbonate decahydrate. Formulas for ionic hydrates are written by appending a vertically centered dot, a coefficient representing the number of water molecules, and the formula for water. The two examples mentioned in the previous paragraph are represented by the formulas. Copper 2 sulfate pentahydrate CuSO 4 bullet operator 5H2O. Sodium carbonate decahydrate Na2CO 3 bullet operator 10H2O. Nomenclature prefixes. Number prefix. 1 sometimes omitted mono 6 hexa. 2-di-7 heptax 4 tetra 9 none 5 penta 10 decax. Table 2.13. Qs. C. GAN. D. Magnesium sulfate 7H2O. E. Titanium 3 sulfate. Solution. The anions in these compounds have a fixed negative charge, S2-, Se2-, N3-, and SO42-, and the compounds must be neutral. Because the total number of positive charges in each compound must equal the total number of negative charges, the positive ions must be Fe3+, Cu2+, Ga3+, Mg2+, and Ti3+. These charges are used in the names of the metal ions: A. Iron 3 sulfide, B. Copper 2 selenide, C. Gallium 3 nitride, D. Magnesium sulfate heptahydrate, E. Titanium 3 sulfate. Check your learning. Write the formulas of the following ionic compounds: A. Chromium 3 phosphide, B. Mercury 2 sulfide, C. Manganese 2 phosphate, D. Copper I oxide, E. Iron 3 chloride dihydrate. Answer: A. CrP, B. HGS, C. Manganese 2 phosphate, D. Copper 1 oxide, E. Iron 3 chloride 2 H2O. Chemistry in everyday life. Aaron Brockovich and chromium contamination. In the early 1990s, legal file clerk Aaron Brockovich, figure 2.32, discovered a high rate of serious illnesses in the small town of Hinckley, California. Her investigation eventually linked the illnesses to groundwater contaminated by Crossing 6, used by Pacific Gas and Electric, PG&E, to fight corrosion in a nearby natural gas pipeline. As dramatized in the film Aaron Brockovich, for which Julia Roberts won an Oscar, Aaron and lawyer Edward Masry sued PG&E for contaminating the water near Hinckley in 1993. The settlement they won in 1996, $333 million, was the largest amount ever awarded for a direct action lawsuit in the U.S. at that time. Figure A shows a photo of Aaron Brockovich. Figure B shows a 3D ball and stick model of chromate. Chromate has a chromium atom at its center that forms bonds with 4 oxygen atoms each. 2 of the oxygen atoms form single bonds with the chromium atom, while the other 2 form double bonds each. The structure of dichromate consists of 2 chromate ions that are bonded and share one of their oxygen atoms, to which each chromate atom has a single bond. Figure 2.32a Aaron Brockovich found that Crossing 6, used by PG&E, had contaminated the Hinckley, California water supply, B. The Crossing 6 ion is often present in water as the polyatomic ions chromate, CrO42- left, and dichromate, Cr2O72-. Right. Chromium compounds are widely used in industry, such as for chrome plating, in dye making, as preservatives, and to prevent corrosion in cooling tower water, as occurred near Hinckley. In the environment, chromium exists primarily in either the Crossing 3 or Crossing 6 forms. Crossing 3, an ingredient of many vitamin and nutritional supplements, forms compounds that are not very soluble in water, and it has low toxicity. But Crossing 6 is much more toxic and forms compounds that are reasonably soluble in water. Exposure to small amounts of Crossing 6 can lead to damage of the respiratory, gastrointestinal, and immune systems, as well as the kidneys, liver, blood, and skin. Despite cleanup efforts, Crossing 6 groundwater contamination remains a problem in Hinckley and other locations across the globe. A 2010 study by the Environmental Working Group found that of 35 U.S. cities tested, 31 had higher levels of Crossing 6 in their tap water than the public health goal of 0.02 parts per billion set by the California Environmental Protection Agency. Molecular covalent compounds. The bonding characteristics of inorganic molecular compounds are different from ionic compounds, and they are named using a different system as well. The charges of gamma and anions dictate their ratios in ionic compounds, so specifying the names of the ions provides sufficient information to determine chemical formulas. However, because covalent bonding allows for significant variation in the combination ratios of the atoms in a molecule, the names for molecular compounds must explicitly identify these ratios. Compounds composed of 2 elements. When 2 non-metallic elements form a molecular compound, several combination ratios are often possible. For example, carbon and oxygen can form the compounds CO and CO2. Since these are different substances with different properties, they cannot both have the same name. They cannot both be called carbon oxide. To deal with this situation, we use a naming method that is somewhat similar to that used for ionic compounds, but with added prefixes to specify the numbers of atoms of each element. The name of the more metallic element, the one farther to the left and/or bottom of the periodic table, is first followed by the name of the more non-metallic element, the one farther to the right and/or top, with its ending changed to the suffix "ide." The numbers of atoms of each element are designated by the Greek prefixes shown in Table 2.10. When only one atom of the first element is present, the prefix mono is usually deleted from that part. Thus, Colorado is named carbon monoxide, and CO2 is called carbon dioxide. When two vowels are adjacent, the ending vowel in the Greek prefix is sometimes omitted in common practice, though IUPAC guidelines only permit this for the duplicate letters O in monooxide, which is correctly written as monoxide. For purposes of the nomenclature exercises in this text, students may choose to follow either approach. Some examples demonstrating this. Some other examples are shown in Table 2.11. Names of some molecular compounds composed of two elements. Compound name, So 2-sulfur dioxide BCl3 boron trichloride. So 3-sulfur trioxide SF6 sulfur hexafluoride. Number 2, nitrogen dioxide PF5 phosphorus pentafluoride. N2O4 dinitrogen tetroxide tetraphosphorus decaoxide. N2O5 dinitrogen pentoxide IF7 iodine heptafluoride. Table 2.11. There are a few common names that you will encounter. For example, although NO is often called nitric oxide, its proper name is nitrogen monoxide. Similarly, N2O is known as nitrous oxide, even though our rules would specify the name dinitrogen monoxide. And H2O is usually called water, not dihydrogen monoxide. You should commit to memory the common names of compounds as you encounter them. Example 2.14. Naming covalent compounds. Name the following covalent compounds: A SF6, B N2O3, C dichlorine heptoxide, D P4O6. Solution. Because these compounds consist solely of nonmetals, we use prefixes to designate the number of atoms of each element: A sulfur hexafluoride, B dinitrogen trioxide, C dichlorine heptoxide. Check your learning. Write the formulas for the following compounds: A phosphorus pentachloride, B dinitrogen monoxide, C iodine heptafluoride, D carbon tetrachloride. Answer: A phosphorus pentachloride, B N2O, C IF7, D carbon tetrachloride. Link to learning. The following website provides practice with naming chemical compounds and writing chemical formulas. You can choose binary, polyatomic, and variable charge ionic compounds, as well as molecular compounds. Binary acids. Some compounds containing hydrogen are members of an important class of substances known as acids. The chemistry of these compounds is explored in more detail in later chapters of this text, but for now, it will suffice to note that many acids release hydrogen ions, H+, when dissolved in water. To denote this distinct chemical property, a mixture of water with an acid is given a name derived from the compound's name. If the compound is a binary acid, comprised of hydrogen and one other nonmetallic element, the word hydrogen is changed to the prefix hydro. The other nonmetallic element name is modified by adding the suffix -ic. The word acid is added as a second word. For example, when the gas HCl hydrogen chloride is dissolved in water, the solution is called hydrochloric acid. Several other examples of this nomenclature are shown in Table 2.12. Names of some simple acids. Name of gas, name of acid. HF of G, hydrogen fluoride. HFAQ, hydrofluoric acid. HCl of G, hydrogen chloride. HCl of G, hydrochloric acid. HBrG, hydrogen bromide, AQ, hydrobromic acid. HIG, hydrogen iodide, HIAQ, hydroiodic acid. H2S of G, hydrogen sulfide, H2S of AQ, hydrosulfuric acid. Table 2.12. Oxyacids. Many compounds containing 3 or more elements, such as organic compounds or coordination compounds, are subject to specialized nomenclature rules that you will learn later. However, we will briefly discuss the important compounds known as oxyacids, compounds that contain hydrogen, oxygen, and at least one other element, and are bonded in such a way as to impart acidic properties to the compound. You will learn the details of this in a later chapter. Typical oxyacids consist of hydrogen combined with a polyatomic oxygen-containing ion. To name oxyacids, omit hydrogen. Start with the root name of the anion. Replace ate with IC or ITE with add acid. For example, consider H2CO3, which you might be tempted to call hydrogen carbonate. To name this correctly, hydrogen is omitted. The ate of carbonate is replaced with IC, and acid is added, so its name is carbonic acid. Other examples are given in Table 2.13. There are some exceptions to the general naming method, e.g. H2SO4 is called sulfuric acid, not sulfic acid, and hydrogen sulfite is sulfurous, not sulfyu, acid. Names of common oxyacids. Formula anion, name acid name. HC2H3O2 acetate acetic acid, HNO3 nitrate nitric acid, HNO2 nitrite nitrous acid, hydrogen hypochlorite perchlorate perchloric acid, H2CO3 carbonate carbonic acid, H2SO4 sulfate sulfuric acid, H2SO3 sulfite sulfurous acid, H3PO4 phosphate phosphoric acid,